Hi, and welcome to Module 2 of Lecture 7. In this module, we're going to be discussing dummy variables, or more precisely, when and where to use dummy variables and why to capture concepts that you want to understand. And we're going to start with this by looking at an example of what is the effect of partisanship on feelings towards the environment. To answer that, we need to answer the question of how to measure feelings towards the environment. So we asked people to answer this question: which of these responses is closer to the way you feel on a scale of 1 to 5? On one extreme, we say that regulation to protect the environment already places too much of a burden on business. Or, on the other extreme, tougher regulations are necessary to protect the environment. We can form from that answer to that question a dependent variable to scale from 1 to 5 with larger values more in favor of environmental regulation. We want a partisanship variable because that's our key independent variable. So we have a partisanship scale from 0 to 6, with 0 being strong Democrat and 6 being strong Republican. And we have two control variables of income and education. We can do this regression, and we might get results like this. We have the coefficients on our estimates of all our coefficients on each of these variables, and standard errors for each one. The first question is naturally for hypothesis testing: which ones are significant? We can eyeball this. We divide the estimate by the standard error to get a t statistic. We see that this first one on party is going to be definitely greater than 2. Education will also be greater than 2, so these will probably both be significant, given the size of the data set. And income, however, is less than 1, so probably will not be significant. Okay, so that was relatively straightforward. But we're not done there. We also want to understand the magnitude of these effects and what they mean. We interpret these effects, right, these estimates, as holding every other independent variable constant, the effect of the independent variable, like party, on feelings towards the environment. That's what each one means, holding every variable constant. Then we want to maybe predict how these independent variables affect the dependent variable. We've done this before by inserting particular values of all of our independent variables in a multiple regression, and then working out the sum to figure out what our predicted dependent variable is. And we're still going to do the exact same thing here. And we do that often by just assigning the mean value to all the other variables, right? So if we're trying to look at effect sizes for, say, the effect of partisanship x1, we don't want to insert a particular value at random for x2 and x3. Instead, we choose their means. And it tells us what the effect of partisanship is in terms of magnitude and significance, all else being equal. So what we can do is things like comparing a Democrat with an average education and an average income to a Republican with an average education and an average income. Okay. And we can do it like this. So we have our regression equation. We insert our estimates for the constant for beta 1, for beta 2, and beta 3. That's the second bullet point here. We find the mean values for education and income in the sample. We put them here. And then we just go around changing our partisanship variable to compare strong Democrat to independent to weak Republican. And we get these values. Now, we don't have to actually do this, mind you. We could have just said the difference between strong Democrat and independent is 3. 3 spots on this partisanship scale. So we multiply partisanship by 3, and that difference of 3 times this is the difference from here to here. Right? And 2 points from here to here is 2 times this. So we could have just done that. The benefit of doing this out and using the mean values for these other 2 variables is we actually get concrete numbers for prediction instead of just differences between different values of the dependent variable. But wait, this assumes something very strong that's kind of under the hood, hidden under the hood here, which is that the relationship between partisanship and feelings towards the environment is linear, right? That each unit increase in partisanship has the exact same effect on feelings towards the environment, right? And that's not necessarily a true assumption, right? We might think there's not linear, and there's not the same step going from weak Democrat to independent as there is from weak Republican to strong Republican. Maybe there are very different effects. And we can't capture that by using an ordinal single variable for partisanship in that way. So what we can do instead is we can use dummy variables. And to make it simple, we're going to code it to have only Democrats, Republicans, and Independents be 3 different categories. Unlike with turnout, we're going to have 3 categories instead of only 2. So because of that, instead of having only one dummy variable that takes the value of 1 for yes and 0 for no, we need at least 2 dummy variables, with the third being captured by a reference category. Why do we need a reference category? Well, in any case that we have more than one dummy variable, we can't have as many dummy variables as categories. It was kind of natural when we had only one dummy variable. There were actually 2 categories, yes and no, captured by one dummy variable. The same is true as we extend the number of categories we need to capture. If we have 10 categories, we want only 9 dummy variables. And the reason is, in order to estimate coefficients, as we saw before in the last module a little bit, but more in the as we saw in the matrix multiplication module, we discussed matrix multiplication and determinants and inverses. If we have variables that are too closely collinear, that are too closely correlated, or even the same, we cannot then calculate coefficients. Going back to that matrix module, we saw that if we had 2 of the same columns in our matrix capturing the independent variable x, because they're collinear, then we would have a singular matrix. It could not be inverted. X transpose x would be singular. It could not be inverted, and we couldn't calculate our coefficients. In this case, when you have all the possible choices out of a bunch of dummy variables captured, because we know the very last category by the values in the first n-1 categories, that last variable for the last category is perfectly determined by the previous n-1 category's values. So we have perfect collinearity, and we can't manage to run that model, right? So if we have n categories and n variables, those n variables will be perfectly related and will fail to produce a coefficient estimate. So what we do is remove one of the categories and treat that as the reference category. That allows us to get past this problem. Now, it does introduce a limitation, which is if we determine the statistically significant effect for one dummy variable, it is always relative only to the reference category and not to all the other categories that you've included. So in this case, if we have, say, Democrats be the reference category, we are comparing independents to Democrats and Republicans to Democrats, but not independents to Republicans. And we can't do that with the specification in which Democrats are the reference category. We can never make comparisons or inferences about comparisons between other categories other than between the one captured in the dummy variable and the reference category you've chosen. How to choose the reference category? It'd be nice to choose it based on some underlying theory, or to choose based on some underlying interesting comparison you expect to get. But in reality, it's arbitrary. You just pick one. Okay, so now we're going to do the same things before, but now we've condensed our ordinal scale, or split our ordinal scale of partisanship up into 2 dummy variables, one for Republican, one for independent, with the Democrat variable being the reference category. What do we get? Well, again, comparing estimate to standard error, we see that that estimate divided by standard error is way greater than 2, so Republicans are significantly different from Democrats. Now we divide the independent estimate and independence to standard error, and we see it's less than 1, so we do not see that independents are different from Democrats. Already we're finding a reason to use these dummy variables because before we had a constant change in partisanship for each unit, but that turned out to be an illusion. In reality, the effect is not constant. There's no difference we're finding here between independents and Democrats. We are finding a substantial difference, though, between Republicans and Democrats. The last question we could ask, are Republicans different from independents? We can't tell that on this table because we're never comparing Republicans and independents. We're comparing only Republicans to the reference category of Democrats and independents to the reference category of Democrats, and that's it. So now if we wanted to test this last question, we could run the whole thing over again, but now choose a different category of independents as a reference category, and then compare Republicans to independents and Democrats to independents. But in that case, we couldn't have answered this first question if Republicans are different from Democrats. Okay. To calculate predicted values, we have to be careful about what we call the reference category. So again, we're going to treat the same equation as before, but now we have two dummy variables instead of one partisanship variable. We insert our average values for income and education to get this. And now to figure out what kind of party the person is a member of, we put in the appropriate values for dummy variables. A Republican has a 1 in Republican and a 0 in the independent dummy variable. So we see 1 and 0, and we get an estimate of 3.099. The independent has a 0 for Republican and a 1 for independent, and that gives a 3.55. The Democrat is the reference category, so has zeros for both Republican and independent. And that reference category is a 3.63. So we can kind of see why there's a difference between Republican and Democrat, but not independent and Democrat. The difference here is relatively small compared to the difference here. So that's how this works. Just be careful. If you have a reference category, that would be zeros in all the existing dummy variables if you want to predict values for the reference category. Okay. So how does this help us? It helps us overcome the linearity assumption implicit in ordinal variables. If you have an ordinal variable in regression, it's implicit an assumption in that regression that moving from one unit to another unit within that ordinal variable all has the exact same effect on the dependent variable y. If you believe that, great. If you don't believe that, because the ordinal variable means something more complicated, for instance, then you might want to break up the ordinal variable into multiple dummy variables to get around and away from that linearity assumption, that uniform effect assumption. You must use dummy variables to measure categorical variables, as we discussed before, I think. How many to include? The number of categories in your variable minus 1 always, and you can only compare cases to the reference category. Here's one more example to close out this module. Audience, and this is, we're going to do this together. So at home, you should stop, pause, and then try to answer the question before I talk through it. Yeah. So the question is, who knows more about politics? What party members know more about politics? The dependent variable here will be a measure of political knowledge on a scale from 0 to 26. So it's a bunch of questions about what you know about how the political world is at present, knowledge about the world. There'll be independent variables for age, education, and partisanship, and we're going to use dummy variables for partisanship. We're going to treat independents here as the reference category, and Democrats and Republicans as the two dummy variables. The model looks like this. Political knowledge on the left, plus a constant, plus a coefficient times age, plus a coefficient times education, plus 1 times dummy variable for member of the Democratic Party, and plus 1 times the dummy variable for member of the Republican Party, or at least identifying as a member. Here are some results. And here, instead of the standard error, we just directly listed the t-ratio, the t-statistic. So what's significant? Everything, right? They're all really large. These are all significant in this particular regression. Now we can compare. According to the model, who knows more about politics? Now I want you to stop here and pause and answer these questions yourself. I'll pause for a brief second so it's easier to pause for you, and then we'll talk through the answers. Okay, that wasn't too awkward. So, who knows more about politics, a 70-year-old or a 30-year-old? Well, over here we have a positive coefficient on age, which means the older you are, the more you know about politics. Therefore, a 70-year-old on average knows more than a 30-year-old. Remember, from back to the beginning of this course, this is not a deterministic model. This does not mean every 70-year-old knows more than every 30-year-old. This means, on average, controlling for these other variables, we believe a 30-year-old will know less about politics than a 70-year-old. Note it's not much difference, right? 30 times, a 40-year difference is 40 times this coefficient, right? Which is about 2.4 on a 26, on a 26-point scale? On a 26-point scale. Anyway, second question, who knows more, a high school graduate or a college graduate? Again, education is a positive coefficient, has a positive coefficient, so the more education you have, the more you know about politics, holding constant this other stuff. So a college graduate will know more about politics than a high school graduate. Okay, how about a Democrat or independent? Well, a Democrat has a positive coefficient on that dummy variable, so a Democrat will know more about politics than an independent, on average, holding this other stuff constant. Republican or independent? It's Republican, because Republican has a coefficient that's positive as well. So comparing to the reference category, a Republican would know more about politics than an independent would, on average, holding this constant. Finally, a Democrat or Republican, we don't know. It's tempting to look at this plot, to look at this table and say, well, the number here is higher than the number here. 4 is higher than 2, so it's got to be Republican. It might be, but we can't tell from this particular table. We can't tell from these results. If we wanted to test that, we would have to use either Republicans or Democrats as a reference category and then look at the dummy variable for the other one. It's entirely possible that even though we might get a positive value if the Democrats were the reference category and the Republicans were the dummy variable, that might very well not be significant. The difference here is only about 1, and that might not be enough to get you significance given the size of the data set. I don't know. I didn't do that, but we don't know. The point is we do not know from this table, from these results, how to compare a Democrat or Republican to a Republican in terms of political knowledge. You can only ever compare to the reference category. Okay. So let's do some. Let's conclude with some predictions. Let's hold the education constant at 3, and then compare a 30-year Republican, and then predict for a 30-year Republican, a 60-year-old Democrat, and a 40-year-old independent. And again, I'll pause so that you do that yourself before I flip to the next slide. Okay, so to do that, we're going to start. I'm going to skip that for a second. We take age. We take the constant. We add age, the coefficient of age times the age. We add the coefficient of education times 3. Then we add the appropriate dummy variable times the appropriate coefficient. For Republican, we make the Republican dummy 1 and Democratic dummy 0. For the Democrat example, we make the Democrat dummy 1 and the Republican dummy 0. And for the independent, we make them both 0 because that's the reference category. The next slide does that for you. There's the constant in each case. There's the 0.06 times the age, 30, 60, and 40. There's the 2.65 times the constant 3 we held education at. And then for Republican, it's the Republican dummy is 1. For the Democrat dummy is 1. And for the independent, they're both 0. And we see not too much difference here, but substantial difference over here. And that's it. That's how we deal with dummy variables. In the next next module, we're going to discuss the last category of our 2x2 table we dealt with in hypothesis testing, corresponding to cases in which you have a dichotomous dependent variable, like a yes/no question, and a continuous independent variable. Thank you very much.